Our hyperbolic trig functions. Um, this is actually really interesting, and um, just reading this lesson helped me understand the beauty of math. So let's just move on here. So in pre-calc, we learned that a hyperbola is defined as the difference of two variables squared, or not the difference of two variables squared, the difference of the two squared variables is equal to a constant 1. And the reason why I use a and b instead of saying x squared divided by a is because, again, these are arbitrary, so a can be defined as 1 over, whatever you want. So that's why I said that, because I think it would look a lot more complicated if I put it separately, because these are just constant multipliers. So in every other math class, we learned that x squared plus y squared equals 1. You'll learn that in your algebra 2, maybe even algebra 1, and maybe even geometry. Well, just as sine and cosine give you the ratio of the opposite or adjacent to the hypotenuse, so do the hyperbolic trig functions by giving the ratio of any opposite or adjacent to the hypotenuse at any point of the circle. And the beautiful thing about this is that the hypotenuse changes. So somehow these math geniuses figured out a way that they can calculate the Pythagorean theorem and divide each opposite side without even using any sine or cosine or tangent at all. So that's pretty smart. And even just looking into it, um, it's like, how do you even think of that? Like, yeah, it's just pretty smart. So the definition of a hyperbola is proved in precalculus. So if the x squared minus y squared is a constant difference, engineers and mathematicians found a way or a function such that the difference between the squares of the two variables is constant. So much like the original thing where they found sine hx and cosine hx is equal to 1, proved through the Pythagorean theorem. I think I made a proof on that. These guys found a function that's essentially, no matter what numbers you plug in, the squares or the difference of the squares is always just going to be equal to 1, which is pretty genius. And like, again, I think I searched it up. They were solving differential equations or solutions to differential equations. I think it was y double prime plus y prime is equal to 0, and they found like some solution. I don't know. It was just some solution to differential equations, which goes in the future, but that's just kind of the logic behind why they did so. By doing so, they found a way to calculate each x and y position at any point of the hyperbola without even needing the hypotenuse to be constant, which is pretty genius because before, with the x squared plus y squared definition, we just assumed that the hypotenuse was 1 in the unit circle, such that sine x or sine theta is always just going to give you x. So, because the hypotenuse times sine theta always gives you the x component, but because the hypotenuse is 1, hypotenuse times sine theta is just equal to 1 times sine theta. So that's how they defined it. But here, as I mentioned before, they figured out a way such that when you divide they do the Pythagorean theorem calculation, divide it by the ratios, and give you back, the ratios. So at any points, you can calculate the length of, or the opposite divided by adjacent, which is tangent, or opposite divided by hypotenuse. It's just genius, and I would have never thought of something like that. So, like, ever in my entire life. So here we have x squared plus y squared equals 1, which is just sine squared plus cosine squared equals 1. But a little interesting thing here is that the hyperbola is actually the difference of the squared variables, as I've mentioned before, because as we learned, it's ax squared minus bx squared equals 1. So yeah, we'll move on. So for the unit circle up here, that's the definition, and for the unit hyperbola, it's defined here. Unit hyperbola just means that a and b are essentially constant, or a and b are 1. So yeah, that's what that means. So hyperbolic sine x is just these definitions. So yeah. Whoa, okay. Sine hx, which is hyperbolic sine x. I'll just say sine h because I don't want to say hyperbolic all the time. It's just the difference of these two variables divided by 2. Cosine hx is e to the x plus e to the negative x over 2. And you'll realize that this one is even and this one is odd, much like the actual trigonometric functions, the regular trigonometric functions. So that's why you can think of these functions as cousins of the regular trigonometric functions. And of course, tan hx is just a ratio of the two. So again, pretty smart because they figured out a way to relate, you know, sine x, cosine x to these hyperbolic trig functions, which don't even have a sine or cosine. So it's pretty smart. Never would have figured that out. Domain here is negative infinity to infinity. And the range is actually infinity to negative infinity, or negative infinity to infinity, which is quite smart also because, or not quite smart, but in the original trigonometric functions, sine is capped at 1 and negative 1. Same with cosine hx. In fact, sine hx isn't even periodic, which makes sense because you never get the same y value back in a hyperbola unless you go to the negative side. So yeah, it's pretty smart. There, we're actually... Sorry, I'm thinking. No, you don't even get the same value back if you go to the negative side. So that's pretty smart. This is the cosine hx, just switching this to a positive sign. And this one is actually even. So again, the same thing here. This one is just a ratio of the two, so it would be e to the x minus e to the negative x divided by 2 divided by e to the x plus e to the negative x over 2. You can cross the 2 out, do some math there, but yeah, those are the ratios here. These are all the domain and range restrictions. So the other trig functions are just reciprocals, and they are pretty smart because if you see here in the hyperbolic tan function, the range is negative 1 and 1. This is just a reciprocal of that, and guess what? The range is also real numbers below negative and past 1. That's because, or think about this, right? The maximum of these functions are negative 1 and 1. That means the ratio flipped would also just be this one positive, this one negative. So that one is just absolutely pretty smart to me. And then these ones are just things. When I say inclusive, that means it includes the number 1, but these are all the domain and ranges here, which are just, again, reciprocals of these functions. So nothing, pretty hard. Cosine hyperbolic x is always positive. In fact, I actually didn't show you what each function looks like. So let's start with sin hx, and sin hx looks much like a cubic polynomial. So again, you can think of it as taking all the domain and range of the cubic polynomial, which is all real numbers. Cosine hx is quite interesting because it looks like a quadratic function. In fact, you can even kind of model it with x squared plus 1 because the range is 1 to infinity, such that x squared is always positive and the minimum point is x squared. So again, quite genius there. Tan hx is bounded between negative 1 and 1. And actually, the beautiful thing about there is because it looks like the inverse tan function. So it looks like that. So that's pretty beautiful as well. I mean, seriously, there's so much overlap. Here, these are just the identities that are really similar. This one is much like the cosine squared x identity. And the bottom one is just what happens if you divide cosine squared x on both sides. Yeah. And again, the beautiful thing is here, the asymptotes, the vertical asymptotes are still preserved. Here there are no vertical asymptotes. Here there are vertical asymptotes. Yeah. So this is, yeah. It's just logic. Here there are no vertical asymptotes here, but there are vertical asymptotes here. But this one still holds, while this one also still holds for essentially all real numbers. So that's what I think is pretty interesting. Here are all the derivatives here. So the interesting thing is the derivative of sine x is the same. The derivative of cosine x is not the same because you just multiply it by negative 1. From the old trigonometric derivatives, such that it's basically the absolute value of the old trigonometric derivative. The derivative of tan x is secant squared x, so much like the old derivatives, and there are some exceptions, obviously, such as this one right here, but these are just all the derivatives you'll have to memorize. So I don't think I mentioned the catenary. In fact, you can use these functions to model waves, as long as the waves have a constant. I think frequency is what it was. So this one is actually pretty smart as well. I'll show the proof later, but because it will take a pretty long time to show the proof with algebra. The inverse function just comes from solving this backwards, and they actually use quadratic variables to solve for it. So yeah, or the quadratic function, essentially plugging in e to the y variables. So inverse hyperbolic functions are logarithmic, not trigonometric. So again, it doesn't have any signs in there, so that's pretty smart as well. Defined for larger domains than inverse trig, because inverse trig only returns a value of, well, depending on which inverse trig function you use, it's definitely it has less of a domain than the inverse trig function. So yeah, except for tangent, I believe. So these are the derivatives of the inverse trig functions, and in fact, there are some other ones such as inverse cosine h, or inverse the inverse of secant h to the negative 1x. But those are pretty easy because you can just change this to 1 over x, and it would still be the same thing. So these are just hyperbolic trig functions. Quite simple stuff, although it is a completely new topic from what you were taught before, so it can be quite tricky. But just treating it like the cousins of the original trig functions will, essentially grant you the same thing, it's the same logic. So that's it for hyperbolic trig functions.